This is just a short little blip about how I thought we might be able to convert ambient heat energy into useful power output without an initial temperature difference being needed. And we're going to do this by creating a temperature difference, which we can do with a heat pump. Heat pumps move heat energy from point A to point B. When you move that heat energy away from point A will get colder, and when you move it to point B will get hotter. The interesting thing about heat pumps is it actually takes less energy to move heat from point A to point B than it does if you simply converted energy at point B from, say, electrical energy into heat energy. That's why heat pumps can be very efficient forms of heating or cooling. We actually have a rating in EER for energy efficiency ratio, which allows us to quantify how much heat energy in BTUs we are moving per supplied electrical energy in watts per given hour. In a lot of air conditioner units, you actually see this represented as an SEER, which is a seasonal energy efficiency ratio, which is the anticipated yearly average of the different seasonal conditions of that heat pump's instantaneous or shorter term hourly EER rating. In thermodynamics, a dimensionless unit, a COP or coefficient of performance, is used. In that system, the cooling power in watts is in relation to the electrical power in watts. So units are the same type. Converting between an EER to a COP, we need to just divide by 3.413. This is useful for our particular application, which we will see shortly. For example, a high-efficiency rated air conditioning heat pump with an EER of 20 would have a COP of approximately 5.8. This would mean that for every 1 watt-hour of electrical input energy that such a heat pump would move approximately 5.8 watt-hours of heat energy between points A and B. Thus, point A becomes cooler and point A becomes slightly warmer as it moves the heat energy between those 2 points at that expenditure of 1 watt-hour worth of electrical input. To create the largest temperature difference at a specific point, we could use 2 of these types of heat pumps. One pumping to create a colder or less heated area on one side, and the other pumping to create a warmer or hotter position. That will create a temperature difference between those 2 points as we pump the heat energy toward it on one side and away from it on the other. By combining the two, it ends up being 11.6 watt-hours of heat energy moved by spending 2 watt-hours of electrical energy input. Since 11.6 over 2 is still the same COP rating of 5.8, which is convenient. Now that we have a temperature difference between that concentrated hot and cold area, we would need some way of converting that temperature difference into something useful. If we used a heat engine, like a Stirling engine, that would allow us to convert between the temperature difference into mechanical motion. Or if we use a thermoelectric module, that would allow us to convert between the temperature difference directly into electrical energy, depending upon what type of power output we would want. If our conversion of heat energy is going to a heat engine like a Stirling, we could drive a generator to produce electrical power, or we could use the thermoelectric module, which directly converts the heat energy difference, temperature difference, into electrical energy. Once we have the electrical energy, we could then use that electrical energy to drive the heat pumps that created this temperature difference in the first place. In order for that system to work, the efficiency of the heat energy temperature difference conversion to electrical energy step of the process must be greater than the inverse of the COP. In our case, a 5.8 means that that conversion must be greater than about 17% efficiency. Now that we have this potential possibility, it is important to remember that a 17% efficiency from that temperature difference back into an electrical form is not necessarily an easy thing to accomplish. There will be inefficiencies, of course, all along that step process with friction and electrical resistance in wires and things. So to get that 17 would not be a small task. And it is also important to remember that this is not perpetual motion. We are converting some of that ambient heat energy into electrical energy. And if we actually were to beat 17% and then do something else with that electrical energy, we would slowly be draining the heat energy from the area, which would slowly get to become colder and colder until we wouldn't be able to maintain the efficiencies required to maintain a net positive extraction of heat energy. One last thing I did want to mention is that it is important to remember where that ambient heat energy came from in the first place. If you're talking about the ambient heat energy of the Earth's air, then that is the majority of which comes from solar energy from the sun. It would actually be far simpler, far more efficient, far more cost-effective, far easier to simply convert that solar energy into electrical energy any number of other ways. Solar thermal, solar electric, you name them, there's a ton of them that would be far easier and more efficient to do it than this way. This, however, would be at least a possibility to do something one way. Most useful, perhaps, if there were a natural temperature gradient, like, for example, above ground and below ground during different times of the year, or other things like that, where there might be a natural temperature difference occurring, so you would have less energy needed to create as big of a temperature difference.